Now we're going to look at one of the first concepts that we're going to introduce in your calculus class, and that's the concept of limits. It's kind of natural for us to think about limits. I was thinking this morning about, how many points can a basketball team make in a game? There's going to be a limit to that. You could think about, well, if they made a basket, a three-pointer every second or, something, but you could think about that in terms of limits. I don't know the highest number or the highest score in any basketball game, but you could look that up. I'm sure it exists. One of the examples in the book was how tall can a woman get? And the tallest woman on record was 8'1", and that's pretty tall. Is there a limit to that? I look at basketball players, it seems like every year there's somebody that's taller, but you can think in terms of there's got to be a limit. Another example, more concrete example maybe, is I was thinking about some employers, they will match your retirement contributions. So maybe they say, well, we'll match, if you put in $1,000 a year, we'll match up to $1,000. But there's a limit how much they're going to put in. So say you put in $100 into your contribution and your employer puts in $100. Say, the next year you put in $200, the employer puts in $200. And then maybe one year you put in $1,000 and the employer puts in $1,000. But then that's the limit for the employer. So the next year you might put in $1,200, but the employer's only going to put in $1,000 still. So things like that exist. Okay, so just kind of some ideas about what a limit is. Okay, then we'll go on to look at it a little bit more in a mathematical format. So here we have the notation on the left-hand side, and it's read the limit, Lim for limit, as x approaches a. Okay, so that's really important to recognize that part. As x approaches a, and then the limit as x approaches a of f of x. So that's where our function is, and then it equals L, some limit. Okay, so graphically I'm going to do something over here on the right. So let's say we have a picture of a graph, a function we'll say, and say it goes on like this. Okay, and then say this right here represents the value of A. And then over here, the output, if you had an output, now it's not defined at A. The function is not defined at A for what I have drawn. So here's f of x. This is my picture. And we've had graphs like this before. But what we're saying is, as you approach the value A, so coming over here from the left, as you're getting numbers that are closer and closer to that value A, it's approaching an output of L. And if you go the other way, if you approach A from the other direction, as the numbers are getting smaller and smaller, toward A, then it's also approaching that value of L. And so L would be the limit for that function as x approaches A. So picture the notation on the left and then kind of a picture of what's going on the right. Okay, so now we're going to look at an actual function. So this function is a rational function. So we've graphed those before in previous algebra situations. And in this case, if you factor the numerator, factors into x minus 7 times x plus 1 over x minus 7. You might remember a function like this. Anyway, the x minus 7's cancel. And so you get this to simplify to be x plus 1. And also there's a restriction that x cannot equal 7, right? Because that would make the original function undefined. So that, I should have mentioned that at the beginning, but if you look at the original function, we know x can't be 7 because the function wouldn't be defined there, okay? But when we simplify the function, we still are going to have that restriction that x cannot equal 7, but we get this linear function now, x plus 1, which we could actually graph. So, you could make a table of values or use the slope and the intercept. This is linear. But what's going to happen is, let's see, put in some numbers here, 4, 5, right? Just kind of making a table of values in my head. Now at 7, it will not be a value there. It looks like it would be at 8, like if you plugged in 7 into that function, right? And if you put in 8, you would get 9. And if you put in 9, you'd get 10, into that function that we have. And so you get a picture with a hole in it. And we've done things like that before. It's been a while. We didn't maybe do a lot of it, but if you were to graph that function, that rational function, that's what it looks like. So it's linear, but it has a hole in it because it's not defined at 7, okay? So if we were to say, what's the limit, bad notation, just a sec. What's the limit as x approaches 7 of, and then we can say the function. I'm going to use the, well, yeah, I didn't really want to write it out. Oh well. We could say that that equals 8. So you're here, up here at 8, and you're here at 7. It's not defined at 7, it's just the limit as x approaches 7. Okay, so hopefully that example makes some sense. Okay, so there's a definition, I think, on your paper about limit, and that comes from your textbook. But there were a couple things I wanted to point out. So we already talked about the notation, the limit as x approaches a of f of x equals L. A and L are real numbers. So x is approaching some real number, and the limit is also a real number. And it's not at a. It's not the function evaluated at a. That could be something different. But it's the limit as x is approaching a. All right, so I think that's all I wanted to point out there. And then we have an example. They give us an equation, right? They say the limit as, so it's over here, the limit as x approaches 2 of, and then they give us this function, 3x plus 5, equals 11. And all they want us to do is to identify things. So what is a in this case? A is 2. No, I don't want to write it that way. A is 2, right? It says define these. So what is f of x? Well, what's the function that they're giving us? 3x plus 5. And then finally, what's the limit? 11. So there were some examples in the homework where we were doing this. So they just want you to know the pieces, what the notation means. This is kind of the beginnings of calculus here. So, and I think that's going to be it for this video.